What if I told you that the faintest whispers from the universe's birth are passing through you right now?
Ooh, that's a pretty captivating thought.
It really is, and it speaks to the incredible interconnectedness of everything in the cosmos.
Hmm.
So we're diving deep today into the world of ultra-high-energy neutrinos.
Oh,
They're often called ghost particles because they're so elusive.
right.
So we've got a stack of research from the KM3NeT neutrino telescope today.
Okay.
It's submerged deep in the Mediterranean Sea.
Wow, I did not know that.
Yeah, you can kind of imagine it like a giant net,
Okay.
but instead of catching fish, it's trying to snag these almost massless particles
Oh,
that
wow.
rarely interact with anything.
So why is that such a difficult task? Why is it so hard to catch these particles?
Well, neutrinos are kind of like the introverts of the particle world.
Okay.
They have no electric charge, and they have almost no mass.
Oh, wow.
And they just zip through everything, planets, stars, even us,
Really?
without batting an eyelid.
Hmm.
So how do we even know they're there?
Yeah, how can KM3NeT catch something that interacts so rarely?
It's a matter of scale and patience.
I see.
So KM3NeT uses this vast network of sensitive light detectors
Okay.
spread over cubic kilometers of seawater.
Wow, that's a lot of water.
It is. It's a lot of water.
So it must be pretty rare for them to interact with anything, huh?
It is.
How rare are we talking?
Well, imagine you're waiting for a single snowflake to land on your glove in a blizzard.
Okay.
It might take a while,
Yeah.
but eventually one of these neutrinos is going to bump into an atom in the water.
Oh, I see.
And that's what KM3NeT is designed to capture.
So what did they capture?
Well, they recently made a pretty remarkable catch, wouldn't you say?
Oh, I bet.
They detected a neutrino with an energy of 220 PV.
Whoa, hold on. Back up. What is that? 220 PV.
Yeah, so that's 220 million billion electron volts.
Wow. Okay, so that's huge.
It is. It makes it the most energetic neutrino ever observed. Ever.
Wow.
Just to put that into perspective.
Okay.
The particles that are produced by the Large Hadron Collider, the most powerful particle accelerator on Earth, are tens of thousands of times less energetic.
Oh, wow.
Yeah, it's like comparing a firecracker to a supernova.
Okay, so that's truly mind-boggling to think about.
Yeah, it really is.
To think that much energy could be packed into a single subatomic particle.
Right.
It's really amazing, but this raises a pretty significant question, doesn't it?
It does. What is it?
Well, if these neutrinos are so weakly interacting, how did this one gain such an extraordinary amount of energy?
That's the million billion electron volt question, isn't it?
It really is.
It means there's something out there, some cosmic accelerator that's capable of launching these particles with incredible force.
So what could it be? What are the leading contenders for these cosmic accelerators?
Well, the usual suspects are some of the most extreme objects in the universe.
Like what?
So we're talking about active galactic nuclei, or AGN.
Okay.
They're basically supermassive black holes that are just gobbling up matter and spitting out jets of particles.
Oh, wow.
Yeah, you can imagine it like a cosmic whirlpool with a superpowered fire hose attached.
Okay, so that's pretty intense.
It is.
What else?
Then there are gamma-ray bursts, or GRBs.
Okay.
They're the most powerful explosions in the universe.
Wow, even more powerful than the black holes.
They're thought to be linked to collapsing stars or merging neutron stars,
Oh, okay.
and they release more energy in a few seconds than our sun will in its entire lifetime.
Wow, that's incredible.
It really is.
So are those the only suspects? Or are there any other possibilities?
Well, there is another more intriguing possibility that we haven't discussed yet.
Oh, tell me more.
The possibility that these ultra-high-energy neutrinos could be cosmogenic.
Cosmogenic, what does that even mean?
It means they were born from the interaction of ultra-high-energy cosmic rays with the leftover radiation from the Big Bang itself.
So these neutrinos could be carrying messages from the very dawn of time.
They could be.
That's a pretty extraordinary concept to grasp.
It is. It really is.
But how do we differentiate between neutrinos from these different sources? I mean, they're all incredibly energetic.
Right.
And they all travel vast distances across the universe, so how do we know which is which?
That's where things get really interesting.
Okay.
We can't rely on neutrinos alone to tell the whole story.
Oh.
Instead, we have to combine the data from KM3NeT with observations from other telescopes that detect light, gravitational waves, and cosmic rays.
Oh, so we have to use all of our tools
We do.
to piece together the puzzle.
We do. It's like piecing together a giant cosmic puzzle,
Huh, I like that.
with each type of observation giving us a different clue.
Oh, that's cool. So it's like multi-messenger astronomy.
Exactly.
Combining information from different sources to get a more complete picture of the universe.
Exactly.
But let's focus on KM3NeT for a moment. How does this massive underwater telescope actually work? I mean, it's not like we can just stick a giant net in the ocean and wait for neutrinos to get caught.
It's more sophisticated than a net, that's for sure.
Okay.
Imagine strings of highly sensitive light detectors,
Okay.
called DOMs, anchored to the seabed kilometers below the surface.
Wow, kilometers below the surface.
Kilometers below the surface.
That's amazing.
So you're picturing these lines of detectors.
I am.
But what are they actually detecting?
Yeah, neutrinos themselves don't emit light, do they?
You're right, neutrinos don't emit light directly.
Okay.
But here's where it gets really cool.
Okay.
When a neutrino, by some cosmic chance, interacts with a water molecule, it can produce a charged particle, usually a muon.
A muon.
And when that muon travels faster than the speed of light in water.
Wait, hold on.
Yeah.
Faster than the speed of light?
Yeah.
Isn't that impossible?
You're right. Nothing can travel faster than the speed of light in a vacuum.
Okay.
But in a medium like water, light slows down a bit.
Okay.
And it's possible for particles to exceed that slowed down speed.
Oh, I see.
And when they do, they create a kind of shock wave of light called Cherenkov radiation.
So it's like a sonic boom, but for light. Oh, that's so cool.
And KM3NeT's DOMs are designed to detect this faint blue flash of Cherenkov radiation.
I see.
Each DOM acts like a digital eye, constantly scanning for these telltale flashes.
So each flash indicates a neutrino interaction.
Precisely.
Okay.
And by analyzing the pattern of flashes across multiple DOMs, scientists can reconstruct the path of the muon and therefore the path of the original neutrino.
Oh, wow. So they can actually track where it came from.
They can. It's like tracing the trajectory of a bullet by the sparks it leaves behind.
That's incredible. That's such a feat of detective work.
It is.
But it seems like finding these faint flashes in a vast ocean would be like searching for a needle in a haystack.
It's definitely a challenge, but the sheer scale of KM3NeT increases the odds of catching these rare interactions.
That makes sense.
And the more neutrinos we detect, the more we can learn about their sources and the extreme physics at play in the universe.
So KM3NeT is a bit like a time machine, allowing us to look back at events that happened millions or even billions of years ago.
It is.
It's also a window into the most extreme environments in the cosmos.
Yeah.
Places where the laws of physics are pushed to their limits.
Right.
It makes you wonder, doesn't it? What other secrets are these ghostly particles hiding?
It really does.
Hmm.
It really does. Yeah. It's a bit like we're cosmic archaeologists using these neutrinos to dig up clues about the universe's past.
Mm.
But it's not just about looking back in time. It's also about understanding the incredible forces that shape the cosmos.
Right, and those forces are often unleashed in some of the most extreme environments imaginable.
Right.
We've talked about active galactic nuclei,
Yeah.
those supermassive black holes with their swirling disks of matter and powerful jets of particles.
Right. Those are the cosmic whirlpools with fire hoses we were discussing.
Exactly.
But how do those environments actually produce these ultra-high-energy neutrinos?
Well, the current thinking is that protons, those positively charged particles found in atomic nuclei,
Right.
they're being accelerated to extremely high energies within these jets.
So like a cosmic particle accelerator.
Exactly, but on a scale that dwarfs anything we could build on Earth.
Wow. So we've got these supercharged protons zipping around at nearly the speed of light.
Right.
What happens next? How do those protons turn into neutrinos?
Well, these protons don't just zip around in isolation.
Right.
They interact with other particles and even with photons, those particles of light.
Right. Okay.
And when a high-energy proton collides with another particle, or a photon,
Yeah.
it can create a cascade of new particles, including pions.
Okay, pions, we've mentioned those before. They're subatomic particles.
Right.
But what's their significance in this whole neutrino story?
Pions are kind of like unstable messengers.
Okay.
They decay very quickly.
Right.
And one of their decay products is neutrinos.
Ah, okay. So by detecting neutrinos, we're essentially tracing back to those high-energy collisions.
Exactly.
Those moments of extreme particle creation.
It's like finding a footprint in the sand and knowing that someone walked there even if you didn't see them.
Wow, that's a great analogy.
So these pions are a telltale sign of those cosmic particle accelerators,
Okay.
those extreme environments where neutrinos are born.
But we've also mentioned gamma ray bursts, or GRBs.
Right.
Those seems even more violent than AGN.
They are.
How do they fit into this neutrino picture?
Gamma ray bursts are kind of like the universe's fireworks displays.
Okay.
Incredibly bright and incredibly short-lived.
Right.
They're thought to be associated with the death throes of madwift stars or the collisions of neutron stars.
Yo.
And in those moments of cosmic cataclysm, particles are accelerated to incredible energies,
Oh, wow.
leading to the same kinds of processes we see in AGN,
Right.
collisions, pion creation, and ultimately neutrino production.
So whether it's a black hole devouring matter or a star collapsing in on itself, the underlying mechanism for creating these ultra-high-energy neutrinos is similar.
It is. It's all about accelerating particles to extreme speeds and letting them collide.
But if these processes are happening all over the universe, shouldn't we be seeing neutrinos raining down on us from all directions?
That's a great question, and the answer is we are constantly bombarded by neutrinos.
Really?
But most of them are low energy.
Oh, okay.
and pass through us without a trace.
So it's only the ultra-high-energy neutrinos,
Right.
the ones carrying the signatures of those extreme events that we can detect with telescopes like KM3NeT.
Exactly. They're like the rare, valuable gems hidden in a vast mine of ordinary rocks.
So KM3NeT is sifting through this constant stream of neutrinos, trying to pick out the ones that tell the most interesting stories.
Exactly.
But how do we know which story each neutrino is telling?
Right.
How do we differentiate between a neutrino from an AGM,
Right.
a neutrino from a GRB,
Right.
and a neutrino from, say, the interaction of a cosmic ray with the Big Bang's afterglow?
That's where the detective work gets really tricky.
Be it bad.
We have to look at the neutrino's energy, its direction of arrival, and
Right.
even its flavor.
Flavor.
You see, neutrinos come in 3 varieties, or flavors: electron, muon, and tau.
Neutrinos come in different flavors like ice cream.
It's not quite like ice cream,
Okay.
but the analogy helps to visualize it.
Right.
Think of it like light.
Okay.
Light comes in different colors,
Yeah.
but it's still light.
Right.
Neutrinos have different flavors,
Okay.
but they're still neutrinos.
Okay.
And just like different colors of light tell us different things,
Right.
different flavors of neutrinos can reveal different aspects of the cosmic events that produced them.
So KM3NeT is primarily detecting muon neutrinos because they produce those long-lived muons
Right.
that create the Cherenkov radiation we can see.
Exactly.
But if we could detect the other flavors as well,
Yes.
would that give us even more information about these cosmic events?
Absolutely. It's like having different witnesses to a crime.
Okay.
Each witness might have a slightly different perspective, a
Right.
different piece of the puzzle.
Okay.
And by combining those perspectives,
Right.
we can get a more complete picture of what happened.
So in a sense, we're not just studying neutrinos, we're studying the entire history and evolution of the universe, all encoded in these tiny ghostly particles.
That's right. And it's not just about the past.
Oh.
Neutrinos might also hold clues about the future of the universe.
Really?
For example, they could help us understand the nature of dark matter,
Dark matter.
which makes up a significant portion of the universe but remains one of the biggest mysteries in modern physics.
It's incredible to think that something so tiny and elusive could have such profound implications for our understanding of the cosmos.
It just goes to show that the universe is full of surprises.
It is.
And often the most significant discoveries come from the most unexpected places.
Yeah, I like that.
But speaking of unexpected places,
Yeah.
we haven't delved into the possibility of those cosmogenic neutrinos, the ones born from the interaction of cosmic rays with the Big Bang's afterglow.
That's right. We've mentioned them a few times, but we haven't really explored what makes them so special and what challenges we face in detecting them.
Well, those are tales for another time.
Okay.
Perhaps as we delve further into the mysteries that these ghostly messengers from the cosmos continue to unveil.
It's amazing to think that we've been talking about these tiny particles, neutrinos, for a while now, and yet they hold the potential to unlock some of the biggest secrets of the universe.
Yeah, they're like tiny time capsules carrying information about events that happened billions of years ago from the most distant corners of the cosmos.
And some of those time capsules might even contain messages from the very beginning of the universe, right? We've touched on the idea of cosmogenic neutrinos, but I think it's time we unpack that a bit further. What makes them different from the neutrinos we've been discussing so far?
Well, the key difference lies in their origin. The neutrinos we've talked about, the ones from AGN and GRBs, are born from the interactions of particles within those extreme environments. Cosmogenic neutrinos, on the other hand, are created when ultra-high-energy cosmic rays, mostly protons, collide with photons from the cosmic microwave background radiation, the afterglow of the Big Bang.
So instead of a black hole or a collapsing star, the birthplace of these neutrinos is the leftover energy from the universe's creation. But isn't the energy of the cosmic microwave background incredibly low? I mean, the universe has expanded and cooled a lot since the Big Bang. How could those collisions produce such high-energy neutrinos?
That's a great point. The energy of individual CMB photon is indeed incredibly low. But remember, we're talking about ultra-high-energy cosmic rays hitting those photons. And those cosmic rays can have energies millions of times higher than anything we can create in a lab. So it's the energy of the cosmic ray that gets transferred to the neutrino.
So it's like a tiny billiard ball hitting a giant bowling ball. The bowling ball might not move much, but the billiard ball will go flying off with a lot of energy. But if cosmogenic neutrinos are so energetic, why haven't we detected them already? We've been talking about ultra-high-energy neutrinos this whole time.
That's where the challenge lies. While cosmogenic neutrinos can be incredibly energetic, they're also incredibly rare. The flux, or the number of these neutrinos we expect to see, is much lower than the flux from AGN or GRBs. It's like looking for a specific grain of sand on a vast beach.
So we're not just dealing with a needle in a haystack, we're dealing with a specific, incredibly rare needle in a haystack filled with other, more common needles. That sounds incredibly difficult.
It is, and that's why we need telescopes like KM3NeT with its massive detection volume to even have a chance of finding these elusive particles, but the payoff would be enormous.
What kind of payoff are we talking about? What could these cosmogenic neutrinos tell us that we don't already know?
Well, for starters, they could help us solve the mystery of the origin of ultra-high-energy cosmic rays. We know these cosmic rays exist, we can detect them, but we don't know where they come from. Cosmogenic neutrinos are like fingerprints, carrying information about the processes that created those cosmic rays.
So it's like a cosmic detective story. We have the evidence, the ultra-high energy cosmic rays, but we need to find the culprit, the source that created them. And the cosmogenic neutrinos are the clues that could lead us to the answer.
Exactly, but it goes beyond that. Cosmogenic neutrinos could also give us insights into the evolution of the universe, the large-scale structure of the cosmos, and even the properties of dark matter. They're like messengers from the early universe, carrying whispers of secrets that have been hidden for billions of years.
It's mind-blowing to think that these tiny particles could hold the key to understanding such profound mysteries. It really underscores the interconnectedness of everything in the universe, from the smallest subatomic particles to the largest cosmic structures.
And it highlights the power of human ingenuity, our ability to build instruments like KM3NeT and decode the messages that the universe is sending us. Who knows what other secrets these ghostly particles will reveal in the years to come?
It seems like every time we think we're getting close to understanding the universe, it throws us a curveball, a new mystery to unravel. And often, those mysteries lead us to even more profound and unexpected discoveries.
Yeah, the quest for knowledge is a never-ending journey, and with each step we take, the universe reveals itself to be even more vast, more complex, and more awe-inspiring than we could have imagined.
Well, on that note of cosmic wonder, I think it's time for us to wrap up this deep dive. If you'd like to learn more about neutrinos, KM3NeT, or the mysteries of the high-energy universe, we'll include links to some fascinating resources in the show notes. And as always, we encourage you to keep exploring, keep questioning, and keep looking up at the stars. Who knows what wonders await us out there in the vast expanse of the cosmos?